Thanks very much. It's a pleasure to be here and to give the opening plenary to this conference. I'm going to be talking about cosmic shear cosmology measured from the final release of the Kilodegree survey, KIDS. And as you can see on this nice little animation that's been playing here, this is the footprint of the full area of the Kilodegree survey on sky, painted over the top of the Planck dust map. And this particular map is what we call a Kappa map. It shows the essential combination of all structures as measured by the weak lensing measurements in KIDS. I'm not going to talk about the Kappa maps because the things I'm here to talk about today is cosmic shear. And so I'm going to give, for the non-experts, a very quick introduction into what I'm going to be talking about today. So this is very much the fundamentals of cosmic shear. You can consider this to be the world's smallest cosmic shear survey. This is a cosmic shear survey that's combined of two source galaxies, which are up here in the background. And the light from those source galaxies propagates through the universe, and as the light propagates through the universe, it passes through large-scale structures. So there's one large-scale structure here, a couple of different large-scale structures here, and then a common large-scale structure here. And the passage of that light through common large-scale structures imprints a common distortion on the observed shapes of the galaxies that we see at the end of the on the observed sky down here. And so the initially uncorrelated shapes of these galaxies are ending up correlated by the passage of light through these common structures. And that passage of light, or that measurement of common structure, is the thing that we call cosmic shear. So making this a little bit more rigorous mathematically, what we measure is what we call the two-point shear correlation function, psi plus minus, which is done in bins of angular separation theta. And what we measure is a projection of the line of sight ellipticity between pairs of galaxies in the tangential direction between pairs of galaxies and in the cross direction between pairs of galaxies, offset from the tangent by 45 degrees. And the really elegant thing about cosmic shear is that this observable we make simply with images. And that observable is two very simple mathematical transformations away from the thing that we actually care about, which is the matter-power spectrum of all matter in the universe. And so we can get from this thing that we want to measure with our cosmological probes or our cosmological parameters to the thing that we observe directly on sky with simply a line of sight integral and a Hankel transform, which takes us from L space into theta space here. But there is one in particular pickle in this story, and that is this g squared chi, and in particular this p chi of chi prime, because that thing there is the source redshift distribution, and that's an observed quantity in our cosmic shear surveys, which means that there is an observed parameter that is embedded in the heart of our modeling, and that turns out to be a little bit of a pickle that we'll talk about quite a bit. When we do this measurement, typically we do this measurement in what we call tomographic bins, approximate line of sight bins, and then we measure this combination of this measurement between pairs of galaxies in bins of angular separation shown on the x-axis of each of these panels, and then we measure for psi plus in the upper triangle here, going out in lines of line of sight distance. So we have the nearest combination of pairs in the same bin, and then we go all the way out to the furthest bin of pairs, and then also all of the cross combinations. This measurement that we make gives us a constraint over particular cosmological parameters. The cosmological parameters that cosmic shear is particularly sensitive to are those of omega m, the total amount of matter in the universe, and sigma 8, the clustering strength of that matter. But there's a strong degeneracy between these two parameters in cosmic shear. Essentially, what this means is that if we have very little mass in the universe, and that mass is highly clustered, then we see the same cosmic shear signal as if we have lots of matter that is weakly clustered. And so generally when we do cosmic shear measurements, we parameterize out this degeneracy into a new parameter, which we call S8, that you can see is described here on the slide. Now, S8 is essentially an approximation to the optimum constraining power that we have for cosmic shear. It turns out that sometimes there is still some residual degeneracy with this square root removal of omega m here. And so often you'll also see, and you'll see in this talk, the parameterization capital sigma 8, where instead of assuming a 0.5 for the power of this term, we instead have a free parameter alpha that we fit. And that allows us to remove any residual degeneracy like you can see in the pink contours here. The contours that you can see on this slide are the previous results from Asghari et al. 2021, which were from the fourth data release of the Kilodegree survey, called KIDS 1000, covering 1,000 square degrees on sky. What I'm going to be presenting is the final release of KIDS, the kids' legacy analysis. But before I do that, I want to land on one last thing, which is about the way in which you do robust cosmic shear measurements. Essentially, in order to do robust cosmic shear, you need to do 4 things well. You need to be able to measure shapes. If you can't measure shapes, you can't measure the correlation between shapes, and you can't measure the shear correlation function. You need to be able to measure the source redshift distribution, and this is related to the embedded term in the modeling that I referred to. And in particular, we parameterize the distribution of source redshifts using the average of the redshift distribution, which I've shown here as mean z est, which is going to be relevant in a slide's time or so. You need to be able to model the source galaxy populations, and this is because, as I said earlier, if we make the assumption that the source galaxy population shapes are completely uncorrelated on sky, then all's good in the hood. All things are rather easy. However, if there are intrinsic correlations between the source galaxies in your sample, then that will cause you to over or underestimate the value of your cosmological parameters if you don't correctly remove that spurious signal. And so modeling the source galaxy population for what we call intrinsic alignments is very, very important. And then lastly, you need to understand what baryons are doing, because baryons have this annoying habit of getting in each other's way, and they puff up the dark matter distribution of large-scale structures along the line of sight. And so if we don't correctly model the behavior of baryons, then we overestimate or underestimate, depending on which way you go, the clustering strength of the dark matter that we have. So these are the things that you need to do cosmic shear well. And I'm going to focus on that mean z est for a second, because this is a really important part of our analysis. So we have this source redshift distribution estimate up here. What happens if we get that source redshift distribution estimate wrong? Let's say that we have a true redshift distribution of our source galaxies that reside up here in the background of our slide at mean z true. And instead, we make a misestimate of where those sources actually lie along the line of sight to be much closer to us in the universe. And we have this mean z est. Now, because we make that error in the mean redshift determination, that doesn't change the observations we make on sky. It doesn't change the way in which we model baryons, and it doesn't change the way in which we model intrinsic alignments. And so we see the same signal, but we attribute that signal as coming from a much shorter line of sight in the universe. And that naturally means that we have to interpret that there is a lot more structure in the universe than there actually is, which is a bias in the cosmological parameter we care about, S8. So estimating the mean redshift of our distributions is really, really important. And that's where we get to cosmic shear with kids and with the final data release of the cosmic shear of the kilodegree survey. The final data release of kids, DR5, is more than just an increase in area. Kids 1000, DR4 was 1000 square degrees. DR5 is 1347 square degrees, which seems like a relatively paltry increase in area, all things considered. But DR5 is much more than just an increase in area. It is a full re-reduction of the imaging used for the measurement of our cosmology, including added depth in one of the very important bands, the I band, that we use for line of sight distribution estimation. We've increased the number of tomographic bins that we use from 5 to 6, adding more high redshift information, which is really important and useful, because if we go back to the slide where I had the signals, you'll see that the signal here is climbing as we go to higher and higher redshift, which makes sense, because if light has traveled through more large-scale structure, there is a stronger cosmic shear signal imprinted upon it. And so having higher redshift tomographic bins is really useful to us. We also have additional redshift distribution estimation methods and calibrations that I'm going to talk about. We have new simulations for modeling those distributions and the bias in those distributions. And we've also made some developments with our analysis infrastructure that I won't talk about today. The analysis, as is commonly done in the literature at the moment, quite rightly so, it was done fully blinded, and we analyzed 3 blinds, which are shown here, blind A, B, and C, which are shown for one of our particular statistics, which is called Casabi's. It's essentially just a reweighting of that shear correlation function that I was talking about earlier. And you can see it compared to Planck in the red contours. Now, the 3 blinds variously agree completely with Kids 1000, agree completely with Planck, and sit in the middle ground where we don't know one way or the other. And so naturally, everyone in the survey thought that it was going to be the boring one in the middle, but it turns out that Kids' legacy was unblinded and we had full agreement with Planck. And to put that into context, in this S8 parameter, we have agreement with Planck that is consistent at 0.7 sigma. You can see the number up here. But as you can see, there's also a considerable degeneracy still present in the S8 parameter, which is why we opted for most of the papers, most of the analysis, to instead refer to capital sigma 8, which is our most constraining parameter. And you can see that in capital sigma 8, our constraints with regards to Planck are consistent at 0.73 sigma. And the different points that I'm showing here are just different ways of summarizing your posterior from your Markov chain Monte Carlo. This is for one of our statistics for the Casabes. We also have another contour that you can see here in purple, which is for another way of calculate or reweighting your shear correlation functions, which are called band powers, and you can see those are also consistent with the results from Planck. Furthermore, at the end of Kids' Legacy, we then ask the question, how does this agree with the landscape of Stage 3 cosmic shear surveys as they currently stand? And as you can see, the constraints from cosmic shear with Kids' Legacy are in very good agreement with the constraints from DES Year 3, and we're very, very much looking forward to the DES Year 6 analyses, which is coming out imminently, or so the water cooler says. And are also formally in agreement with the results from HSC Y3. Formal agreement here being less than 2.3 sigma in marginal one-tailed distributions. And so this paints the picture of Stage 3 surveys that are largely in agreement with one another, and in the case of Kids' Legacy are in full agreement, and the Dark Energy Survey are in agreement with Planck. We also, in the course of the Kids' Legacy analysis, went then about a joint analysis, and the joint analysis leveraged both a combination with the Dark Energy Survey's Y3 analysis, which was made very easy by the analysis that predated that, which was a Kids 1000 combination with DES Y3. But we also combined with other probes from DESI and Pantheon plus supernovae in order to make a constraint on S8, which you can see listed here, which is the most precise measurement of S8 that has been made to date. And so we're very excited about the results from cosmic shear at the end of Stage 3, really seeming to come into agreement with what we see from the CMB, which I appreciate is somewhat at odds with the form of the title of this meeting. So we've somewhat removed one tension with the analysis of Kids' Legacy. That then obviously begs a very important question, which is what happened? We went from Kids 1000, where we had an analysis that showed a greater than 3 sigma difference with the results from Planck from the CMB, and we ended up with a result from Kids' Legacy that was in full agreement with Planck. And so when we unblinded and we found out that we were in agreement with Planck, we went, that's going to require some explanation. And so we then took some time before releasing the papers and went through a very forensic analysis of determining exactly which change went through and led to the variations that we see in our estimated cosmological parameters. So this is the analysis from Asghari et al. You can see is different from Planck at 3.75 sigma. There was an analysis in 2023 by Shunsheng Li et al., where he, amongst other things, updated the scale cuts that were used for Kids 1000, and that update to the scale cuts removed some of the tension with Planck and brought it down to 2.93 sigma. And this is where we then took the data from for Kids 1000 and then reanalyzed a full catalogs to cosmology reanalysis of Kids 1000, and we used instead the N of Z estimation methods that we've developed for Kids' Legacy, and we find that those N of Z estimation methods pull the S8 tension down a little bit louder. That's okay, I'll just try and speak a bit softer. And the next thing that we did was we analyzed the impact of adding in new calibration data, and that new calibration data that we add in pulls the tension down again by down to 1.6 sigma. And this is before we even ask the question of what happens with the new Kids' Legacy area, Kids' Legacy data. This is just adding in methods and new calibration data. We then added in the actual images and photometric redshift estimates from Kids 1000, from Kids' Legacy, and that pulls us a little bit further down to 1.17 sigma. If we add in new 6th tomographic bin measurements and we change the intrinsic alignment modeling to our fiducial intrinsic alignment modeling, you see that doesn't change S8 very much, but it does increase your constraining power, which pulls all of the error bars down, and that increases the tension again slightly. And then lastly, if we add in the additional area, then that gives us an additional shift upwards to brings us into our final value of 0.73 sigma. So I'm going to talk about a few of these points today. I'm not going to have time to go through the developments of all of the things that we changed in Kids Legacy, but I will focus about the change to the spectroscopic calibration method and the estimation of our N of Z, and lastly about some of the changes to our imaging. So in Kids Legacy, we estimate redshift distributions in a similar way to what is done commonly in the literature in Kids 1000 and also in DES Y3 using a self-organizing map. This is a projection of an n-dimensional color space down into 2 dimensions. And you can and we then fill that color space with calibrating sources. So these sources over here are the calibrating spectra for which we know the true redshift of our sources. This is the distribution in color space of our wide field shear measurements, which we don't have true redshifts for. And we essentially reweight the distributions in color space so that the representation in this space matches this space, and that gives us our redshift distribution. We then perform this same analysis on detailed image simulations that have all of the complexities of our data in order to estimate the bias that's present in those redshift distribution estimates, and then we use those for our cosmological inference. So how is this improved in Kids Legacy? So we've moved on from one class of our estimation method, which we called gold class, into a new thing that we call gold weight. So this is our self-organizing map colored by true redshift. And one of the things that happens when you populate a SOM like this with calibrating spectra is you find that there are areas of the color space that do not contain calibrators. And those areas are pathological because if you don't have a calibrator, then you cannot contribute those sources to your final estimated redshift distributions. And so those sources are typically removed, and those are the orange cells that you can see here would be all of the wide field shear sources in those cells would be thrown out. And this process we went through in Kids 1000, we called this gold class. And in Kids Legacy, what we realized is that because the self-organizing map training process is a noisy machine learning process, that process is prone to noise in itself. And so if you undergo this process multiple times, you retrain a self-organizing map, you decide whether things are represented or not, and then you repeat the process, what you find is that the average assigned gold class over many realizations is actually a continuum. It's not 1 or 0 for every single source every time because there is noise in the training process. And so you can use that continuous variable, which we call gold weight, to now assign a weight, an additional weight to the sources for how well represented they are in their color space by the calibrators. And one of the nice things about gold weight is you can see if you cast your eye to now the map that I've trained here and colored by gold weight, is that the gold weight value correlates with true redshift. So there are patches here where there is lower coverage, which follows the expected redshift areas of the redshift axis of the self-organizing map. Said differently, that means that the gold weight is reflecting accurately that there is systematic incompleteness in the redshift calibration sample in a way that gold class was doing only approximately and in a very noisy way. This is one of the main improvements that we have made. Another significant improvement that we've made is to greatly increase the number of calibrators that we have access to. And this was done and able to be done because of a dedicated campaign that we made on making Kids and Viking or imaging like the kilodegree survey in deep calibration fields of spectroscopy. And here you can see those fields listed on Sky. A more relevant point is these fields listed in right ascension and redshift, so you can actually see the calibrating spectra that we have access to. This is the distribution of all calibrating spectra that were available to us in the Kids 1000 analysis of Kids DR4, and this is the distribution of calibrating spectra that we have access to in DR5. It's more than a 5-fold increase in calibrators, which greatly increases the availability of our calibration sample to correctly identify the sources that we need or the redshift distributions that we have for the sample. One of the other things that we've developed is a redundant method of estimating the redshift distributions using spectroscopic cross-correlations, cross-correlating the distribution of on Sky of wide field shear sources and calibrating spectra. And one of the great things about our calibration method now is that the estimates that we have made, this is now on simulations, using our fiducial method, our color-based method, which is this SOM N of Z here, Those N of Z, as I said earlier, are passed through fully realistic image simulations, multi-band image simulations with shear and all that nonsense in it. And those then give us estimates of the bias that we have on our redshift distributions. And that's the blue lines that you can see here for this simulation. We then take a fully independent set of spectroscopic sources that we use for on-sky cross correlations, and we can use those to estimate the bias in an independent fashion that doesn't require the image simulations. And that gives you the red data points here. And as you can see, the red data points fully agree with the SOM N of Z bias. So we have a method of calibrating our redshift distributions that is completely independent and that also returns the same bias that we see on these simulations. We now look at the same thing on the data, and on the data we see a similar level of agreement. There is a slight difference in the biases that are estimated using our cross correlations in a few tomographic bins in the middle, but largely speaking, this agreement is very, very good. And most importantly, if we use the N of Z biases estimated from cross correlations, we find no change in our cosmological parameters. We find an increase in the error bar, which comes from the fact that our estimates here in the 6th tomographic bin with cross correlations are quite poor because we run out of cross correlation calibrators. But largely speaking, this is very, very encouraging. It tells us that our estimates, our redshift distributions are well calibrated in Kids Legacy. We've also made a couple of other redshift distribution updates that I'm not going to go into detail of. One of them is called prior calibration, which is essentially a reweighting of the calibration sample so that it makes it more accurately represents what we expect a wide field shear sample to look like. And we also updated the way in which we define the self-organizing map. We went from one self-organizing map to many in the case of Kids Legacy. And the reason I'm not going to go into those in detail is because, again, they don't make a difference. So the calibration that we have is robust to these sorts of arbitrary changes to the method, which is good. There is one more thing that I'm going to talk about with regards to changes in Kids Legacy, and this is regarding the imaging. As I said, we did a complete reanalysis of the imaging for Kids Legacy, and that meant going all the way back to the imaging, completely redefining the 0-point calibration, the astrometric calibration. And one of the main changes that we did was to update the astrometric calibration to use Gaia. And here you can see the residuals between our astrometric calibration and Gaia stars. So the points here, each point is 1 square degree of Kids. This is the northern hemisphere in the left-hand column, the southern hemisphere in the right-hand column, and you can see the data points here show that our residuals in right ascension and declination are all considerably less than about 0.03 arc seconds. The reason I'm showing you this plot is not so that you will have an intuitive understanding of what 0.03 arc seconds means in terms of a residual, but is so that I can then show you the calibration that we had for previous Kids analyses with Kids 1000, and you can see that those were both more uncertain and more systematically biased with regards to the ground truth of Gaia. And so that means, again, that our imaging has improved under Kids Legacy, and we are more confident that our imaging is robust. One of the things that this improved astrometric calibration brought with it, unfortunately, was a new failure mode that we didn't appreciate until we underwent the cosmological analysis, and we started looking at null tests. And in particular, one null test, which is called a B-mode null test, is a test for a signal that should not exist at the level of stage 3 accuracy in cosmic shear. And as you can see from this upper panel, we measured a B-mode in Kids Legacy at a significance of around 10 to the minus 9, which is fairly highly significant. And so we then went through, again, a bit of a forensic investigation to identify the root cause of this B-mode, which came back to all the way back to the astrometric solution, where we found that the increase in the number of calibrators that we had in Kids Legacy triggered some distortions in areas of lower coverage that were unnatural. And so we then identified a metric, which is this x-axis, that we thought should correlate with the areas impacted by this systematic effect. We then analyzed the survey, my little arrow, we then analyzed the survey using different values and rejecting data based on different values of this threshold. And we found that, yes, indeed, if you threshold on this value and you remove area, then you remove the B-mode signal. And so we selected a particularly nice round value of 0.2 in this metric as our fiducial, and we removed all data where this metric was less than or greater than 0.2. And that meant that we were then able to run an analysis that wasn't affected by B-modes. The crucial point here, though, that we also ran this analysis with our cosmological measurements, and the cosmological measurements are completely insensitive to the presence of this B mode. So even if we had done nothing, we would have seen no systematic bias in our cosmology because of this systematic effect. Nonetheless, we went through the process and removed it anyway because we thought it was the right thing to do. So that brings us to the important question that I've kind of been leaning into the last few slides of how do we know that kids' legacy is more robust? I've given you a few indications based on sort of hand-wavy things that we've improved things, but this is now some quantifiable metrics in which we can analyze how do we know that kids' legacy is more robust than previous work. In particular, in one of our cosmology papers, Stelzner et al., we went through a greatly expanded suite of internal consistency tests, which we used 3 tiers. The first tier was based on evidence-based metrics like Bayes factors and suspiciousness. The second tier was multi-dimensional parameter estimates, where we split the analysis into 2 sections, and then we model with 2 different cosmologies and look at the systematic bias between the 2 different cosmological parameters estimated from one half of the survey and the other to make sure that they agree with one another. And the last metric that we used was a PPD-based metric to check whether or not data vectors measured for one half of the survey or a different half of the survey were consistent with one another. And we then did splits in lots of different ways. So here you can see splits based on redshift bins, so where we isolate one redshift bin and its cross correlations and analyze that with regards to the others. We analyzed autocorrelations versus cross correlations, and we analyzed different scales, different modes, different various other things. We also did a bunch of catalog level splits, so we reanalyzed the entire survey as multiple surveys, where we have a split in the north and the south, and also a split in red versus blue. And in all of these cases, the 2 halves or the different splits are fully consistent with one another. There is no indication in any of the tests that we have done that there is any internal inconsistency with kids' legacy, which is very, very nice. Here's an example of one of the ways that we know kids' legacy is improvement upon the previous work. This is the redshift distributions analyzed independently in Kids 1000 in the way that I was just describing, one correlation versus the others. And you can see here that in particular bin 2 is an outlier. Bin 2 has a systematic difference in its value that seems to be quite a bit higher than the rest of the bins when analyzed on its own. It's important to note that when you remove bin 2, Kids 1000 didn't actually change its cosmological conclusions, which is why this was deemed to be curious but not relevant to the conclusions of the analysis. In Kids Legacy, when we perform the same test, now with 6 tomographic bins, we don't see any outliers. We don't see any tomographic bins that disagree with any other tomographic bins. The results are all very consistent with one another. So that's the analysis that we've got from Kids Legacy. This is the final data release of Kids. That said, there is still ongoing work within the Kilodegree Survey collaboration. There is extended models that are being analyzed at the moment. And 3 times 2-point analyses, 6 times 2-point analyses, combining different probes together with Kids Legacy. So there is more to come from Kids Legacy, so keep an eye out. But this is really the cutting edge that we have from Kids to date. And as you've seen, it also means that according to Kids, the S8 tension is no more. With that, I'll happily take questions.
Questions? Really nice talk, excellent work, great forensics. Can you go back to the slide where you show the shift since 2021?
Yeah.
So yeah, I really liked how you broke this down, but so I like to think of systematics kind of like coin flips, you know, you do the right thing, you do the wrong thing.
Yeah.
But this kind of like you flipped a coin or 7 times and landed the same direction each time.
Yeah.
So what's the through story or covariance of like, how can that be?
So there's a couple of answers to this question, and it's a great question, Dan. And as an astrostatistician, I totally understand the drive to answer this. There are 2 ways to think about this. The first of which is that this story is not random, because firstly, each one of these things builds upon the last, and the story that I've painted out here is not the first way that we came up with this description. This is very much a constructed figure that we made to tell the story of this is the clearest explanation that we have of how the progression goes from one step to the other. If you take these points or these choices that we have here and you permute them, then things jump around in a more chaotic fashion. This is simply designed to tell the story in this way. But the more relevant point for me is that the assumption that we have when we say that we're making random coin flips is that the underlying truth is somewhere here, right? Which is not necessarily the case. If you make the assumption that the underlying truth is somewhere closer to where Planck is, and that what we're doing at each one of these analysis steps is removing systematic bias, then it makes perfect sense that you would march towards the underlying truth. The question then becomes, do you naturally expect all of these systematic biases to remove amplitude? And that's a more complicated discussion. But this is very much designed to demonstrate this marching towards Planck in a very graphical, very sort of in-your-face manner, because we think that redshift calibration is clearly the most important. These steps here, 1, 2, 3, this is basically only changing the n of z, right? And so we really are just playing around with how you calculate and calibrate redshift distributions, and that takes you across the crucial threshold, right? The crucial threshold is 2.3 rather, and if that's all you care about, then nominally the only thing you need to do to reconcile kids and Planck is to update the estimation of the calibration here.
Thanks for the nice talk. Are there any additional systematic biases that could be removed either by this survey or by future surveys?
Yeah, yes. One of the common questions we get asked is given the bias that we saw in Kids 1000 or the difference that we see between Kids 1000 and Kids Legacy, did we underestimate the error bar in Kids 1000? And I think this question is along the same lines, because the analyses that we do are always best effort, excluding all systematic effects that we know about that are present. We cannot exclude the possibility that there are further unknowns that are present in the data set, and that's the whole purpose of next generation surveys. So the next generation analyses from, in particular, Euclid and Rubin and Roman will really, change the game here. And this is a figure from our Data Release 5 paper, which just shows all of the different surveys, cosmic shear surveys, previous and future. And up here in the top corner, you have LSST, Euclid, and the Chinese Space Station Telescope. These are 3 surveys that are going to be doing, in particular, Euclid and LSST are already taking data, and there was the great Rubin announcement last night. And then over here in its own panel is Roman. Roman is really in a game of its own with regards to depth, which is what's shown on the x-axis. But all of these different surveys contribute differently to the systematics landscape. Euclid has the smallest PSF because it's space-based and will really do shape measurement and depth very, very well. LSST has unbelievable depth because of the large size of its mirror, and it also has broader multi-wavelength coverage than Euclid has. And so there's lots of different ways that these surveys contribute to the systematics landscape, and they will answer questions that KIDS and DES and the Hyperspectral Prime Cam survey can't answer. So we think we've got them all, but next generation surveys will tell us, and they're coming. They're already in progress. So it's an exciting time to be part of Cosmic Shear.
We thank Angus again.